So let's talk more specifically then about data types. And this is related. Data are the actual variables, actual variable values, excuse me. Datum, by the way, is the singular of data. Data can come from a population or from a sample. And most importantly, it can take on two different types, qualitative or quantitative. And they are very similar to the types of variables that we just saw. Qualitative data is essentially categorical, and we will often use those terms interchangeably. Quantitative, as you might expect from the name, means it uses numbers. Right? It's a quantity in some sense. It's a measurable kind of thing. Now, in the category of in the grouping of quantitative, there are actually two different types. It can be discrete, or it can be continuous. And if you've taken a lot of pure math classes, you may know what those terms mean, but if you haven't, it's perfectly understandable you might not. This word discrete means in separate chunks, separate groupings. And so an example of a quantitative discrete idea would be something like if I'm counting things, that's quantitative discrete, right? I might have 1 in this group, or 2 in this group, or 3 in this group. But if I'm counting them, I don't have 1.5. Right? If I'm counting people, for instance, the number of people in a classroom, that's a discrete number. There wouldn't be 1.5 people in a classroom, I hope. Continuous, on the other hand, can take on any value in a range. And so things that might be continuous would be things that I might be able to consider stretching across all possible decimal values. Things like pressure, things like temperature. Those would all be continuous data types. Quantitative continuous. All right, so let's do some examples. I want you to tell me whether you think this data type is quantitative or qualitative. And if it's quantitative, I would also like you to tell me whether you think it's continuous or discrete. So let's start with this particular data type. Suppose I'm collecting the number of credits that you are taking this semester. Is that a continuous value, or is that a quantitative or qualitative value?
Quantitative.
Right, it's numerical, and the numbers have actual numerical meaning. And since it's quantitative, we can ask whether it's continuous or discrete. Which one is true here? Discrete, exactly. It is discrete because we are counting how many credits, right? We can't have 2.25 credits. It just doesn't work. What about your current class year?
Qualitative.
Yeah, I would argue that this is qualitative. I know that it's connected to total number of credits, so in a sense, there might be a quantitative component to it. But the categories here, freshman, sophomore, etc., those are literally just grouping people into separate groups. Even if we have a mathematical rule for deciding whether we group them in this group or this group or this group, it's still a qualitative or categorical classification. What about the temperature outside?
Quantitative.
Quantitative. Obviously, I can use numbers to describe that temperature. And which type of quantitative data is it? Continuous or discrete?
Continuous.
Because I don't have to leap from 22 degrees to 23 degrees. 22.1 degrees is perfectly valid. 22.03 degrees is perfectly valid if I have a fine enough measurement system. What about the year you graduated high school?
Qualitative.
Okay. You could think of that as qualitative because, in a sense, we are grouping people into separate groups. Could you think of it as quantitative?
Yeah. Yes.
I would say you could do that too, in the sense that the numbers actually do have meaning as well. If I know your graduation year and I know my graduation year, I can look at the difference between those two things and know immediately how many years apart we graduated. So those numbers do have numerical meaning as well. It's not just a category. So it kind of depends on the use there, which one you would declare this to be. Okay. All right. So for each variable type, there are different ways of representing them visually. And so some common qualitative charts would be things like, we'll see this later, frequency charts or bar charts. And they can convey the same information. Frequency charts do it numerically and listing it out as a table. And then bar charts do it visually by taking the same information and then showing it with a collection of bars here. I did want to tell you this particular information. We'll see some more of this later on in the term. It comes from an old textbook I like to use that had a nice example about passengers on the Titanic. So this is actually the information about first-class passengers, second-class passengers, and so on that ship. And you can see from here that there were many more third-class and crew passengers than there were second and first class. But it's even more easy to understand, easy to recognize the scale of the difference when you see it here visually. This first one is useful if I want to do any calculations with those numbers. And this second one is more useful if I want to just have a quick impression of how is the group distributed. Okay. A couple things I should mention. Excuse me. When you produce a bar chart, which is distinct from a histogram, we'll talk about those later on. A bar chart will always have a space between the bars, and it's for qualitative data. So these are separate categories, and even if they have things like first, second, and third crew, where there is some kind of an ordering I can think of, excuse me, there's no way to average these things. I can't use any mathematical subtraction, addition, things like that to these ideas. So another way we can display it is as a frequency table, and I'm going to go through this relatively quickly because we'll see more detail with a better example later on. But I could look at that same data and ask what percentage are in each category. And again, I can do that as a table or as a frequency chart. And you'll notice this looks like exactly the same image as on this slide. But my vertical scale here is now a percentage, whereas over here it's an actual count. Okay. So the bar chart will do a count, and then a frequency chart will do a percentage. Often this frequency chart is more easily visualized as a pie chart. This is taking the same percentages and putting them in as proportions of the pie. And of course the advantage excuse me, of doing that here is that I can actually include the data from the original frequency count inside each slice of the pie, whilst simultaneously giving the fraction that that pie represents. So that's very helpful. All right. Oops. I guess the pie chart information is not showing up. I'll have to recompile that. I wrote a slide for this, but I guess it didn't compile in. I will include the updated slide in the slides that I post. Sorry, I was finalizing these last night, and just this last one didn't go out. For bar charts, there are two things to keep in mind. If I have, in this case, both frequency charts, if I have a frequency chart for ethnicity, I might alphabetically order the different categories and then graph them here, the bar chart. Or I might rearrange the categories so that they're in decreasing size. Okay? In this second case, it's called a Pareto chart. And that, as you might see, is a little easier to interpret. Right? Looking at this one, they give me the same information. It's the same categories. It's the same amounts. But it's a little easier to interpret this one because I can instantly see which group was the largest, which was the second largest, the third largest, which was the smallest, and so on. Whereas here, it takes a little searching, and I have to be careful comparing these kinds of things, depending on where they might be located. I apologize. My voice is starting to go a little bit, but I'll do my best. All right. Another thing to be aware of about data types is we can measure data in different levels. And the types of statistical procedures that we use depend on what level we're measuring our data on. So it's really important to be able to decide what level of measurement applies to the data that I'm collecting. So the four levels that we will be classifying them in, from lowest to highest, are nominal scale level, ordinal scale level, interval scale level, and ratio scale level. So we're going to spend a little time with each of those. Let's start with nominal. All right. So nominal, if you think about that word, it comes from the Latin word for name. And so like nominee is someone you are naming. Denomination is the name that was given. So the nominal scale level is a qualitative measurement. So I am measuring a category in that case. So that, again, looking back to the example of things you might find on a driver's license, categories that might apply might be eye color, hair color. Those are all categories. And I can still collect that data, put it in a spreadsheet. That could still be a variable, but it would be a qualitative variable or a categorical variable in that case. So that's nominal. Okay? I can put that data into categories. But I can't arrange that data in order. Right? It doesn't make sense to order blue eyes, then brown eyes, and then green or anything like that. It just doesn't work. So instead, the nominal is not orderable. Okay? The example I have here in the slides, if I'm looking at your favorite type of food, maybe one group selects veggie pizza, another group selects vegan sushi, and deciding which one of those comes before the others doesn't have any meaning, really. There's no reasonable way to organize that ordering. So that's what a nominal scale level will have. Ordinal scale level, it opposes an order. That's where the ordinal term comes from. So data is measured using an ordinal scale. It's similar to nominal scale, but there is one important difference. I can order them. And this, I think it's best to think of this as a rank ordering. Okay? So if I asked for instance, the top 5 national parks in the United States, I could list 1 through 5, and there's a big difference between 1 and 5. The order there does matter, but I can't think about subtracting, say, 2 minus 1. Right? The gap between 1 and 2 doesn't have to correspond to the same gap between 2 and 3 and 3 and 4. Right? This rank ordering is not quite the same. I'm giving this is greater than this is greater than this kind of thing, an ordering, but it's not, the difference has no mathematical meaning. Okay? So this is where I can still place them in categories, but I cannot, and I can arrange them in order, but I can't subtract data values. Right? I can't subtract first from third or something like that. And of course can't determine if one data value is a multiple of another. The next is the interval scale level. And so this is similar to ordinal because we can definitely order things. But the difference is, in this case, we have a meaning for subtraction. So temperature is a nice example. It's measured using interval scale. I can think of 40 degrees as the difference between 100 and 60, regardless of which kind of temperature scale I'm using, whether it's Celsius, Fahrenheit, Kelvin, or some others. The differences there actually make sense. And the gap between 60 and 100 is the same as the gap between 0 and 40. So that difference has a mathematical meaning that is consistent. That's a common feature of integral scale measurements. The key thing to pay attention to in deciding between interval and ratio is whether 0 degrees or 0 as a measure is the absolute minimum. Okay? For many things we may look at, 0 is an absolute minimum. GDP, for instance, if I'm measuring the GDP for a country, the gross domestic product, 0 is the minimum. Right? You can't have a negative GDP. Maybe very small, maybe declining in size, but 0 is the minimum. So that's why it would not be interval level. In fact, it would be better. It would be what's called ratio. Okay? Temperature is interval level because 0 is not the absolute lowest temperature. We can, of course, have temperatures below 0. We've had some here recently. Temperatures like negative 10 degrees Fahrenheit or negative 15 degrees Celsius do exist, and they are below 0. So 0 is not my minimum, and therefore interval is the best I can do. So I think I kind of pulled the rug out from under the last one here. Ratio scale level is similar to interval level, but now we do have a 0 point that is the minimum, and we can calculate a ratio between different things. We can always do that. So an example of that might be if I had a statistics class with a multiple choice final exam. This one's not going to be. And maybe I have these 4 scores. If the exams are machine graded, I can put that data in order from lowest to highest. That means it's at least ordinal. The differences between the data have meaning. Right? When I subtract 2 scores, I can tell the difference between the points. And that actually has a mathematical meaning in terms of the performance for each student. And so that means it must be at least interval level. And in this case, I actually can calculate ratios. I can take the 80 divided by 4 to get 20, right? So 80 divided by 20 is 4. So the score of 80 is 4 times better than the score of 20. I can calculate those ratios, and the smallest score is 0. So that means this is actually ratio scale. All right, any questions about those data types? Those levels of measurement. All right, so I did hint earlier that I have a slightly better example for the frequency charts. So I did want to make sure this is clear. This is a problem I've seen students come up with on homework in the past. Some of our questions will ask you to build a frequency table, and then they'll ask about the relative frequency and the cumulative frequency. And so this is hopefully going to outline how to do those things. So in this example, we have 20 students asked how many hours they worked per day. And this is the list of their 20 different responses. Right? You'll see some responses are repeated, and some more often than not than others. And this one is unique. This 7 only happened once. So this is what's called a frequency table. And that's where I list out the different data values that I observed. Each one has a different row. And in the next column, I simply give the frequency, which is a count. How many times did I observe that particular data value? The 3 here tells me there were 3 values of 2 in my data set. The 5 says there were 5 values equal to 3. There were 3 4s, there were 6 5s, there were 2 6s, and 1 7. So this frequency you can think of as just a count. We do, if there's an ordering for the data values, by the way, we do them in that order. So in this case, it's in ascending order. We could do descending if we prefer that, but usually ascending is the easiest way to go. Relative frequency is kind of like converting from that count to a percentage or to a proportion. So, for instance, going from the same data, there were 3 2s, and there were 20 total values. 20 total data values. So that particular grouping, the values that were equal to 2, was 3 of the 20. And if I compute that fraction, that comes out to 0.15, so I might also call that 15%. So the relative frequency here is the 15%. Similarly, for the 3s, there were 5 of those, and so that corresponds to 5 out of the 20, which is 1/4 for 25%. The 4s correspond to 3 out of 20, the 5s correspond to 6 out of 20, and so on. If you give this as a fraction, I prefer them to be reduced, but it's not absolutely required, and I think most of the homework questions will accept a non-reduced frequency, but most will also accept a decimal value if it's exact. Now the last column here is what's called cumulative relative frequency. And when we think of cumulative, think of that as what has accumulated so far. So I said earlier about this course, the final exam is a cumulative final exam. Essentially, we will be covering everything you've seen up to the end of the term. So it accumulates all of the content from the course. The same idea is what applies here to cumulative relative frequency. In this column, I'm going to add up all the frequencies that I've seen so far. By the time I get to the very end of the data, I should have seen everything. So my total cumulative relative frequency in the last row should always be 1 or 100%. I've seen everything at that point. My first column here, we said that that was a relative frequency of 15%, and that's why 15% is my cumulative relative frequency. Thus far, I've seen 15% of the data. The second row is the next 25%. So when I add those two things together, the 15% that I saw already and the 25% I just saw, that gives me a total of 40% here. So the cumulative relative frequency by the data value 3 is 40%. Once I add in the values from 4, that's another 15%, so I'm up to 55% at that point, and then 85%, 95%, and 100%. The calculations are shown here just so you understand what's happening, but in MyOpenMath or on paper, when you produce these frequency, relative frequency, and cumulative relative frequency charts, you don't have to include those calculations. You can simply put in the answers. This is to make clear where those answers came from. Okay? All we're doing is we're adding up everything we've seen so far. The 55% is 15% plus 25% plus 15%. Any questions about that? All right. So I think that's a good time to take another break.